So now we can continue. Uh, we are tackling at number 9. So the positively charged rod attracts the negative charges, electrons, that is the electrons, and repels the positive charges. When Earth, the electrons flow from Earth and neutralize the positive charges. So if it is the positive charges are now neutralized, then it retains the negative charges. The force on a conductor carrying a current in a field can be varied by changing, among others, the magnitude of the current and the magnitude and the magnetic field strength. Name other factors that can be changed to vary the force. So we have the angle at which the conductor cuts the magnetic field. We still have the length of the conductor. Our question 11. The table below carries information on the type of radiation detector and the use of some electromagnetic radiation. Then you're told, fill the blank spaces. Fill the blank spaces. So now we have the microwave. It can be detected by use of crystal detector, solid state diodes. Then you are told, give one use. A use of the microwave. It is used in the radar. Used in the radar. It can also be used in remote sensing. It can also be used in wireless networks. We have an unmentioned radiation. Its detector is thermopile or blackened bulb thermometer. Then it is used for warmth sensation. This one is the infrared radiation. The figure below shows a convex mirror and a plane mirror of equal aperture. Then now you're told, by sketching a pair of incident and reflected rays for each A, B, show how the convex mirror provides the eye a wider field of view than a plane mirror. So we are going to start with the reflected rays. It is advisable to start with the reflected rays. And therefore, if you start with the plane mirror, then we can give some reflected rays like this. So these are the reflected rays. Remember, they are the ones that will help in measurement of the of the image. Then now, from the law of reflection, from the laws of reflection, then you're supposed to apply them so that you can get the incident rays. So that you can get the incident rays. So you're supposed to apply the laws of reflection so that you can get the incident rays like that. Ensure you show the direction. Is now okay. So when it comes to the convex mirror, you also start with the the reflected rays. So these are the reflected rays. These are the incident rays. You'll find that this is now the field of view compared to this one. So you'll find that this one is larger. So the one for the convex mirror is larger. Then our question 13, water is flowing in a very narrow stream from a water tap or a faucet. A negatively charged plastic strip is held close to the stream of water as shown. The stream of water moves towards the plastic strip. Explain this observation. This is like some charges are induced. The negative charges induces positive charges on water by repelling the negative charges. This causes the stream to be attracted toward the rod. Now we are moving to section B. Distinguish between transverse waves and longitudinal waves. This is by definition So I can say that transverse waves they are waves in which the vibration of the particles causing the wave are perpendicular to the wave direction. While for a longitudinal wave, longitudinal, yeah, waves in which the vibration of the particles causing the wave move parallel to the wave direction. Move to the wave direction. Then you are told plain water waves travel from a deep end into a shallow end in a swimming pool at a velocity of 4 meters per second. So this one is from deep to a shallow. So if we can start interpreting, we can draw it like this. So this is a deep, shallow end. Then you're told if the wavelength of these waves in deep is 6 and at the shallow is 1.5, determine the velocity of these waves in the shallow end. So in this one, we are going to use the ratios. So taking the ratios that velocity 1 over V2 will be the same as wave 1 over wave 2. So we are want V1 to be the one for deep, the velocity at the deep, and this one is for the shallow. The same applies to this one, the wavelength at the deep, wavelength at the shallow. Therefore, so I can say V1 from the question is 6 centimeters, which is equivalent to 0.06 meters. So this is supposed to be the wavelength. Supposed to be the wavelength. This is supposed to be the wavelength one. Then our wavelength loop is 1.5 centimeters, which is 0.015 meters. Then now we can substitute and say that our velocity 1 which is V1 was 4 meters. Then our V2 is our question. So we can say that 4, we are substituting in this equation now. 4 divided by V2 is equals to 0.06 divided by 0.015. So my V2 will be the same as 4 times 0.015 divided by 0.06. And my V2 is somewhere missing. The plain water travels from deep end into a shallow end. Plain waves travels from a deep end to a shallow end at a velocity of 4 meters per second. Mhm. There is something that is not adding up. 4 times 0.015 divided by 0.06. Okay, so at long last, we are going to get 1 meter per second from this working. So it is now correct. It is a move, a good move. So now, let's look at something here on what variates. When it is moving from the deep to the shallow, we can see that the velocity is decreasing. So the velocity here, velocity is decreasing. The wavelength is also decreasing. But from the formula of V is equals to F lambda, we know that the frequency will be retained. So whatever changes is the lambda and the V. So in deep ends, higher velocity. In the shallow end, we have the lower velocity. State one factor that affects the velocity of sound in a solid. We have temperature. Of the solids. We have the density of the solid. A disk siren with 200 volts is rotated at constant speed, making 0.5 revolutions per second. If air is blown towards the holes, calculate the frequency of the sound produced. In this case, the frequency will be given by the number of holes times the number of revolutions. And this will be 200 times 0.5. So you're going to get 100 hertz. The wavelength of the sound produced if the velocity is 340 meters per second. Velocity is given by F lambda. So we have the V, we have the F. What is missing is the lambda. Therefore, we can say that our 340 will be given by a frequency of 100 times lambda. So making the lambda the subject of the formula, then it becomes 340 divided by 100, and you get lambda as 3.4 meters. Then your hands state one way of reducing echoes in a room. Echoes in a room are produced as a result of reverberation. And therefore, you can do several ways by covering seats. You can also cover the walls. Can also cover the floor and the ceiling with soft sound absorbing materials. Remember, this is Kapsabet boys. Now we are at question 15. State one advantage of alkaline accumulator over lead acid accumulator. In alkaline accumulator, large currents can be withdrawn over a short period of time. But two, they require little attention. To maintain. We still have others. They are light, and because we are comparing, they are lighter, easily portable. They can stay in uncharged condition. They can in uncharged condition for long time. Our part B, we are told that we are having some resistors in a circuit. Then you are told, calculate the current through the 4 ohm resistor. Here we have the 4 ohm resistor. We have 3, we have 6. The first thing is to calculate the effective resistance of the circuit. Therefore, resistors in parallel, then it will be 3 times 6 divided by 3 plus 6. This is 18 divided by 9. You get 2 ohms. Then, if this is now 2 ohms, then it will be in series with the 4 ohm. So, RT now, it will be 4 plus 2, you get 6 ohms. Like that. So now, from that working, we can now calculate the current. So current will be given by the voltage over the resistance. And this is 3 divided by 6. You get 0.5 amperes. So this will be the current through the 4 ohm resistor. And also in combination of the 3 ohm and the 6 ohm, they are going to share the 0.5 amperes current. We're having a graph here. The table shows the voltage relationship for a certain bit. For a certain bit. So you can see the way it is. Then I'll just write the questions here. The first one, you are told determine the EMF from the graph. You are told to determine the EMF of the cell. And number 2, you are told to determine the internal resistance. So now in this case, there is something that you are supposed to do that you will be able to answer these questions. This one is 1 mark and this one is 3 marks. So from the graph, you're going to get 4 marks. So this is voltage against current. We need to interpret things right here. So the first thing is, we know that from the equation that EMF is given by the potential difference plus IR. Then you are supposed to make this equation to match the graph where our V will become the Y. So we are supposed to match Y is equals to MX plus C, the equation of a straight line. So our V becomes the Y. So V is equals to negative IR plus E, like that. The X is the content or the values in the X-axis, and in our X-axis, we are having the current, this one. So this means that our gradient will be giving us negative R. So the first thing, can say that our slope will be giving us negative R. Then number 2, our EMF will be the same as the Y, supposed to be the y-intercepts, yes, the y-intercepts. So from these two, then we can relate. So the first one is about the EMF. So how do we get the y-intercepts? The first thing is you complete this graph. So I'm going to extend like that. So I'm supposed to read what is here. And this is going to give me, from the scaling, these 10 boxes, 1, 2, okay, 10 boxes are represent 0.5. So it means that 1 is equivalent to 0.05. Now, we have gone up to 3. So we'll have 1, 2, and the third box. So there will be 3 times 0.05, and this is going to give me 0.15. So 0.15, I'm going to add to 1.5, and it is going to give me 1.65 volts. 1.65 volts. Then our part 2, we are asked about the internal resistance. Therefore, I'm supposed to give or calculate the the grounded. So where am I going to pick my points? I'll be picking my points as what you can see from my presentation. Like that. So my slope will be, this is value of 1 minus value of 0.25, then over, this is supposed to be 0.15. So this becomes 0.16 minus 0.35. 0.35. And this is the same as 0.75 divided by negative 0.19. And this gives me negative 3.95. And we had said that our slope is giving us negative IR. So negative R is equals to negative 3.95. Therefore, R becomes 3.95 ohms. That becomes our value. So the EMF here, we have seen that it is 1.65 volts, and this one is 3.95 ohms. So in case you want to know how, just get back to my presentation above. You can proceed. You are told that two coils T and S are wound on a soft iron core as shown. You are told that T has 1,000 tons, while S has 600 tons. And here we have resistance of 100 ohms. Then you are asked, calculate the maximum current measured by the ammeter. The ammeter is on S. So if you analyze the question, this will be the primary. You can say that NP is equals to 1,000 tons. The N secondary will be 600 tons. We have our voltage at the primary case is 250. Then we can calculate the voltage at the first case. So we use the formula of NP over NS equals to VP over Vs. So we have 1,000. Now we are substituting over 600 is equals to Vp we have said it is 250 divided by Vs that we don't know. So it means that our voltage at the secondary will be given by 250 times 600 divided by 1000, and we get 150 volts. Now, since we are looking for the current, from the Ohm's law, V can be given by IR. So this is now the secondary, and this is the current at the secondary. So you can say that 150 volts will be given by the unknown current at the secondary coil times resistance of 100 ohms. So my IS is given by 150 divided by 100. You arrive at 1.5 amperes. That will be the current through the secondary coil. Our question 16, the figure below shows a simple cathode form of cathode ray tube, which produces a sharp shadow of a Maltese cross on a fluorescent screen. Then the first question you are told, explain what is meant by cathode rays. This is just a string, is a string of electrons emitted from a metal surface by the ionic emission. Then, since it is forming a shadow here, then you will ask, what property of cathode rays does the figure illustrate? It shows or it illustrates that cathode rays, they travel in a straight line. They travel in a straight line. State one factor that affects photoelectric emission from a given metal surface. We have the density of the radiation. We have energy of radiation. We have the type of metal. A graph of kinetic energy of photoelectrons emitted by a metal surface A against the frequency of radiation used is as shown below. Then you are told, it's just from the graph. You are told from the graph, you give the significance of the gradient of the graph and what is the significance of OX. You need to analyze this one from the Hastings equation. The original equation was supposed to be energy of a photon is given by the work function plus kinetic energy. Then if we make the kinetic energy to match, to make it, to rewrite this equation to match y is equals to mx plus c, Then from the graph, our Ke becomes the subject. So Ke will be given by energy minus work function. How do we write energy and work function? Kinetic energy will be given by HF minus HF naught. So from this one, we'll be able to respond to these questions. So the first one, we are told, what is the significance of the gradient? So if we match this one, y is equals to mx plus c, then x is giving me the frequency, then my gradient will be giving the Planck's constant. So I can say it gives the Planck's constant h. What is the significance of OX? It's like you're being asked about the y-intercept. My y-intercept is given or carrying a value of negative work function. So a negative work function versus a negative value, then you're going to get the work function in joules. The negative work function in joules. The threshold frequency of potassium is 5.37 times 10 raised to the power 14 amps. When the surface of potassium is illuminated by incident radiation from a source, photoelectrons are emitted with a speed of 7.9 times 10 raised to the power 5 meters per second. Given that the Planck's constant is 6.62 times 10 raised to the power negative 34 joule seconds, and the mass of electron is 9 times 10 raised to the power negative 31 kg, and you are told you calculate the work function for the potassium. Work function is given by Planck constant times the threshold frequency. And this gives me 6.62 times 10 raised to the power negative 34 times the threshold frequency is 5.37 times 10 raised to the power 14. And I'm going to get 3.55 joules like that. Then our part 2, you are told to calculate the frequency of the incident radiation. You are told to calculate the frequency So we are now responding to this question. From energy of a photon, HF is given by the work function HF naught plus kinetic energy, which can be given by half MEV squared. Then this is what we are looking. 6.62 times 10 raised to the power negative 34 times a frequency that we are looking for, F is equals to the work function, this one, we have already calculated from the first question, 3.55 times 10 raised to the power negative 19 plus half times the mass of electron is 9 times 10 raised to power negative 31 times the velocity is 7.9 times 10 raised to power 5 meters per second, and this one is supposed to be squared. So this part, or of this one, is supposed to be giving me 2.808 times 10 raised to power negative 19 joules. Therefore, I can say my 6.62 times 10 raised to power negative 34 times F is equals to 3.55 times 10 raised to power negative 19 plus 2.808 times 10 raised to power negative 19. So if I want to remain with F on this side, then I'll divide through by F by 6.62. So I remain with my F on this side, then I'll divide here by 6.62 times 10 raised to power negative 34. Then my F will lead me to 9.604 times 10 raised to power 14 hertz. That will be the value of the incident frequency. Yes, so this is that. We have our question 17. We are given that diagram over there. This is just the hex ring. So our D, we have the X ring. This is the filament. This is the cathode. We have the lead. We have this one as a beam of electrons. We have the metal targets. This becomes the anode. We have cooling fins. Then now I can start responding. What is A and H? A is the cooling fins. And we have H as the cathode. Let me warn you, if you write A, if you write your answer as, cathode, and then you write cooling fins, without specifying it is A or H, then you get it wrong. But if you write cathode, it is my part H, and then cooling fins as my part A, then you get. So if you don't give them in in the respectiveness of the question, then ensure you specify. Why is tungsten or molybdenum metal most suitable materials for making part C? We are talking of the metal targets. We are talking of the metal targets. They have very high melting points. And the purpose is to withstand high temperature. Remember, there is the surface which is being hit by the high precision moving electrons. Why is part B made of thick copper metal? Part B is the cathode. Remember, we have production of a lot of heat from the connected metal targets. So it ensures to ensure efficient dissipation of it. Why should the machine be surrounded by material G? Remember, from the material G, we said it is lead. Then to absorb the stray X-rays. The stray X-rays. Which would otherwise affect the X-ray tube operator. Why is the tube evacuated? Why is the tube evacuated? To prevent electrons from losing energy due to collision with air molecules. What effect will an increase in current at F on X-ray produced? Increasing current on on F. This is the 18 filaments. So if you increase the current, we are being asked, what will be the effect on the X-ray produced? First thing, we know that increasing the current, the 18 current, that means that a lot of heat will be produced. This in turn increases the number of electrons being dislodged, and this increase the intensity of the X-rays. We can say that the intensity of X-rays will be increased. What about the increasing the potential difference between B and F on the X-ray? So if you increase the potential difference, you are going to produce and X-rays of very short wavelength. So, in case you want to touch, especially, allow me use a different shades. If you want to look at the quantity of X-rays, which is now the intensity, the only part that you can alter is the current. And then if you want to do with quality, which is also the strength of the X-rays, you can only alter the potential difference. In the quality, that is where we find the hard and the soft X-rays. So since now the potential difference has been increased, and X-rays are being produced. So this is just mentioned as a by the way, because you can find the question tuned otherwise. Said one way in which cooling is achieved in X-ray machine. From the diagram, we have seen cooling fins. So we have efficient cooling fins outside the tube. Then we have circulating oil. Through the channels in the copper anodes. State one difference between a capacitor and a cell. A capacitor stores electric charge. A cell converts chemical energy to electrical energy. Also say capacitor discharges instantly, while a cell runs for a longer time. You're having a diagram here where you're told to scale the electrostatic fields pattern due to the arrangement of the charges shown. We know that the fields, electric field lines flow from the positive charges towards the negative charges. So So if you give it the directions, then it will be perfect. Like that. The diagram shows a parallel plate capacitor with a dielectric material in between the plates. We have that diagram. It shows a parallel plate capacitor with dielectric material in between the plates. Set of the following quantities are affected when dielectric material is pulled out of the parallel plates. The potential difference across the plates. The potential difference increases when the dielectric material is pulled out. The charge on the plates, it remains unchanged. The charge remains unchanged. The capacitance of the system decreases. Three capacitors of 1.5 microfarad, 2 microfarad, and 3 microfarad are connected in series to a PD of 12 volts. Find the total charge stored in the arrangement. So the first step is to get the total capacitance. Therefore, we can say they are in series. So 1 over CT will be given by 1 over C1 plus 1 over C2 plus 1 over C3. 1 over CT will be given by 1 over 1.5 plus 1 over 2 plus 1 over 3. So 1 over CT will be given by, the LCM here will be of 6. So from 1.5 we go 4 times. From 2 we go 3 times. From 3 we go 2 times. This gives me 1 over CT will be the same as 9 out of 6. Meaning that CT will be the same as 6 out of 9, which is equal to 0.0, sorry, 0.667 microfarads. 0.667 microfarad. Now we get the charge from the formula that charge Q is given by capacitance times voltage. And we must use this one in SI units, which is 0.667. You multiply by 10 raised to power negative 6. Then you multiply by 12. So that you get 8.004 coulombs. 8.004 coulombs. We are almost getting done. The figure below shows capacitor C being charged. Then you are told what would be observed in the following switch is closed. So we are having our switch here. What will happen to the milliammeter? This one. We expect it to deflect to maximum. it deflects to maximum, then drops to 0, then gradually to 0. What about the voltmeter? You can see it is at the capacitor. Then it increases from 0 to maximum. And the maximum here in this case will be of 4.5 volts. So from the 4.5, it is charging the capacitor. So everything from the 4.5 volts will be drained into the capacitor. Then it attains 4.5. Explain how the capacitor is charged. This will be a narration. We have been awarded 2 marks. This is just some narration. So negative charges flow from negative, flow from negative terminal of the battery to the plates connected to it. At the same time, negative charges flow from the other plates towards the positive terminal. At long last, equal positive and negative charges on the plates creates a potential difference. Creates a potential difference. Then the last part, we have on the axis provided gauge of voltage against time when you are charging a capacitor. So from what we said, it gradually moves from 0 up to maximum. Then ensure at this point, when at maximum, your curve flattens. So, best wishes to physics students. On your coming paper 2. Let's just from ascending case. May it be of very great impact until you just good paper, doing the final touches. Thank you so much.